All right, hey everyone, welcome to this week's ITS Friday seminar. I'm really happy to introduce today's speaker, Dr. Greg Rowangould, who is an associate professor in civil and environmental engineering at the University of Vermont, where he is also the director of the Transportation Research Center. University of Vermont is a partner with UC Davis in the National Center for Sustainable Transportation, as well as our new first set climate grants that we are just launching. Greg's claim to fame for Greg is that he is a UC Davis PhD graduate, not from TTP, but civil and environmental engineering. Yeah, we always love having our students come back, share with us the kind of work they've been doing since they got out of here. So Greg does a lot of different kinds of things. I think air quality is kind of the most constant thing in your career, but very much with an equity focus. So that's what we're here about today. But given his location in Vermont, also a focus on the needs, mobility needs of rural areas and small communities, and how do we improve sustainability in those kinds of places that are so far dependent? Really big, important question. And he's kind of leading the NCST effort on that question. And then he also did some bicycling.
Yeah.
Back when he was, especially.
We have a bike paper at TRB this year.
Oh, you do? That's great. Okay.
NCST funded.
Yeah. Cool. All right, so please join me in welcoming back Greg.
Thanks, Susan. All right, so just going to talk about air quality and electric vehicles and some work we're doing in that area. And I'm going to kind of tell you the story about how I ended up with this project that we're right in the middle of right now. But it started the moment I left UC Davis and went to work for the Natural Resources Defense Council down in LA. So we're going to step through and go quickly over some of the older stuff, but it's yeah, so that's what we're going to do. But before we do that, we acknowledge that this work has presenting today, it's been going on for, I guess, since 2011. So it's been quite a while. Lots of people have worked on it. With these two students, one's now a postdoc who retired, she was a PhD student, so Brittany and Meg, and it's been funded, this project's been funded by a different collection of people over the years, including the Environmental Defense Fund, NCST, EPA, and NRDC, where I used to work, is where I started what I'm about to show you. And, so those are the funders, and before we get that, just a little bit more about myself. So like Susan mentioned, I'm a professor or associate professor at the University of Vermont in civil and environmental engineering. My only degree in civil and environmental engineering is from here, from UC Davis. But I'm a generalist. A lot of my background is in economics. I was a microelectronics engineer for a while in semiconductors. I started in forestry at the University of Maine. So I've done a lot of different things, and but trying to think about sustainability and environment and the theme all along the way. And so there's that. This is Burlington. Look as good on that screen as it does on my computer. It's a beautiful campus, so if you're a master's student, you might think about checking out our PhD program. But it's on a hill overlooking Lake Champlain and the Adirondack Mountains. You have this nice city. I'm a year-round bike commuter, and this is my daily commute route. Down, we have this really nice bike paths to the woods that get from where I live to the campus. And I used to have to haul my kids up to daycare at the campus, but they ride their own bikes now. And sometimes it looks like this. So we go year round. And
It is
sometimes
quite a
it-
feat to be a year-round commuter.
sometimes it looks like that. It's a little more challenging. But e-bikes are pretty heavy, so you put some studded snow tires on them. They work. So I'm normally able to bike every day, but like about 5 days a year. If there's too much snow, it's too dangerous. But mostly because of cars. If there were no cars, I'd bike every day for sure. But okay, so that's just a little background. All right, so we're going to talk about air quality today. We're going to be focusing on air pollution near roadways, and vehicles contribute air pollution, like sort of what we call primary emissions, or sort of the direct emissions that come out of the tailpipe and from brake and tire wear that tend to accumulate near the roadway, which isn't surprising, right? But vehicle emissions also contribute to broader air pollution. So we call that, there's like regional air quality concerns like smog and things like that, which are secondary air pollution. So the emissions from the vehicle mix together, react with other air pollution, sunlight, and all these things create other emissions. So today, though, everything I am going to talk about is these directly emitted air pollutants along the roadways. And when we think about equity, environmental justice, these are important emissions to consider because they form hotspots in very localized areas. And so, understanding where those are is part of trying to understand and look at these equity questions. But there's also this more regional air pollution component too. And that's another thing, and we're not going to be talking about that much today. So just you might keep that in mind. This is work that was done by Dr. Alex Karner. We went to school together here also, and I did this really nice meta-analysis showing just the emissions, these directly emitted air pollutants from vehicles accumulate around within 100 to 500 meters of a roadway. Lots of studies looking at the health effects of exposure to these emissions. And every year there's sort of more and more evidence of these causal links between exposure to air pollution and a number of undesirable health outcomes. And it's well known that there are serious environmental justice concerns, equity concerns with exposure to environmental risks, generally to air pollution and to vehicle traffic emissions. And these are just some papers that get cited a lot, but we know all this stuff. So I just want to put it out there. So we know there's air pollution near roads. We know it's bad for you. People study this. We know there's equity problem. So that's the background, the quick lit review. So why did I start studying who lives near traffic? So this is a story that starts pretty much in the first few weeks of my first real job getting out of college, and working at the Natural Resources Defense Council, which was a pretty sweet gig. The office is a block off the beach in downtown Santa Monica. My apartment was a few more blocks from that. There was a surfboard rack, and it's very nice. My job at NRDC, I was a science fellow, and my role was to advise the litigation team there, the lawyers, on issues to do with air pollution, vehicle traffic, and the idea was it was a 2-year appointment, sort of like a postdoc, that I could be objective and say, you should aim your efforts at suing these people, maybe not those people. I'm trying to give some advice like that. And what happened during that time was,
Maybe tell them what NRDC is.
oh yeah, maybe. The Natural Resources Defense Council. It's an environmental nonprofit.
Very important one.
Yeah, so it's one of the biggest ones. So Sierra Club, the Environmental Defense Fund, another funder of this work, another environmental nonprofit, and the Natural Resources Defense Council, sort of like the big three. And NRDC and EDF were instrumental in creating the Clean Water Act and the Clean Air Act. So that's sort of the history of these organizations. They've been, the Chevron thing that just went down came from NRDC lawsuit. They've been pretty active. And Yeah, so that's what I was working. I work with the litigation team. So these are lawyers that are just experts in litigation and sue to stop crappy projects. So I try to help them find the good ones. And then dig up some of the scientific evidence. So one thing that happened while I was there was this controversy. There was a new truck emission rule that CARB put out. However, there were some miscalculations in the that went into designing that policy, and also some fraud in the person responsible for it. Said they had a PhD from UC Davis, but didn't. So combination of things meant that the rule got rolled back. But this was really important. This is a big deal for communities around the ports across state, that this diesel truck rule was to address environmental justice concerns. And so although some of the technical analysis to support the standard was flawed, we were arguing that, well, let's fix it, not just scrap it. And we argued that it was an important environmental justice issue. However, a high up person in state government pointed out to us on a call that rich people live by freeways too, so don't make it an environmental justice. And so I'm in my new role. The first thing they asked me to do is, Greg, is this true? Right? Well, and this is Santa Monica. There's definitely rich people living next to this highway. I'm like, well, I mean, of course, right? But I mean, in general, it's probably lower income people. People of color probably are living closer to these bigger roads. But I'm like, we can find that. So that's where this all started, was to figure it out. And so why we're going about figuring, so we want to answer this question. They say, who lives near the highways? How do we find air? What's too close? How many people live too? And we started looking at this for California. And we're like, well, we could do this for California. We could just do this for the whole country while we're at it, because the data we were going to use was available nationwide. So that's what we did. So we took data from the HPMS. It's a Highway Performance Management System. It's a national data set together by federal highways. States submit the data there. It's the little black strips you see across the highway, the pneumatic tubes that count vehicles. There's automatic sensors. And so it's traffic counts, average annual daily traffic. And this data is estimated on all roadways, all public roads in the country, except for low volume rural roads and residential urban streets. Everything else has traffic count. And they have about, for 50% of the roadways, they have traffic counts that are specific for medium duty vehicles and heavy duty vehicles. And so we had to fill in some of the missing roads just using the ratio of heavy duty and medium duty vehicles to all vehicles in nearby roads, kind of extrapolate. I'm going to talk more about that later. But this was our main data set. So we got this data and we came up with two metrics. One was we drew buffers around every one of these roadways. And we went out a few hundred meters in 100-meter steps following Alex's paper that showed the concentration of emissions in roads got about 500 meters. And then we created buffers for different traffic volume thresholds, with 25,000 vehicles per day being sort of the lower end of where you might see health impacts. And this was based on literature at the time, that's the limit of epidemiology studies and things that showed, measurable health impacts at that level. Then we just kind of went up. And so we took all these buffers, we intersected it with census data at the block level and figured out how many people live in each of these buffers, and by race, by income, ethnicity. So that's our traffic proximity metric. And then we also came up with something else which we call traffic density. So we took each census block in the country and we drew a buffer around it. So that orange thing is a census block. And then we have this 250-meter buffer, and we add up all the traffic occurring in that area and divide it by the land area of the block. So it's a measure of what we call it traffic density, but so it's another way to think about how much traffic's around. The advantage of this method is like we didn't have to define cut points of distance and traffic volumes. It's a continuous metric and we can calculate for every census block. And then we can look at how this metric varies with the demographics of the census. So this was our second metric, and this is just kind of it's kind of what traffic density looks like. So we zoom in, like Denver here. All these little squares are blocks. So you see it's really granular data, and you can see the different patterns of traffic here. So when we put all that together, what we find is about 25% of the population of the US lives near a road, within close enough proximity of a road with enough vehicle traffic that there should be measurable health impacts of that. And these are studies from a paper we just published last year. Back when I was at NRDC, we published an earlier version of this. So we just did a 10-year update where we added on looking at trucks as well, and a few other things we need to. But so a quarter of the population, just by health is being impacted by being close to these high volume roads. When we looked at those traffic density values, we sort census blocks into 10 groups. We'll call them deciles, right? So the lowest 10% by traffic density, the next 10, the next 10. And if you look at the population within each of those groups, the census blocks with the lowest amount of traffic density have very few people of color, right? And as you go up to places with the most traffic, there's a much higher share of people of color. And we have this data plots by every race and ethnic group, but just to kind of sum everything up, we just have non-white here. And you can see that trend, just kind of a linear trend, and it's a huge difference, right? Going from about 20% all the way up to 60%. Income, we see a similar pattern. There's a little uptick at the end, which is largely a result of cities being somewhat more expensive places to live. People make more, but don't necessarily have more money. So to look at those plots nationwide, what we did is for every county, we fit a regression to the traffic density value versus the demographic of that block. So in this case, it's the percent of the population that's non-white and median household income. And these maps that are behind here are the slope of that line fit, basically. And we're just showing the color for the ones that are statistically significant. So this is a way to see the strength of that relationship with traffic density and the share of a particular population group, and test its statistical significance, and then be able to look at it all at once. Okay. So up on the top here, and LDV is light duty vehicles, medium duty vehicles, heavy duty vehicles. And so the red coloring is showing this disparity where people of color are more likely to live somewhere with more or higher, there's a positive association with traffic density. And there's a negative correlation with traffic density and income with the blue shading on the bottom. And what you can see from these figures is that these inequities, these disproportionate exposure to traffic, occur in almost every single county. It turns out it's like 85% of the counties. So it's not just like a California thing or, here or there, it's everywhere. And this, we didn't expect to find this when we first did this, that it's so prevalent. And it's kind of amazing, not in a good way. And so, the takeaways here were roads with, higher traffic volume and more traffic are located more likely to be located where people of color and people with lower incomes live. And these disparities, they're everywhere. It's pretty much everywhere you look. So that was the first study. And what we've done more recently was so that was NRDC supported that work. Environmental Defense Fund called me up, another big environmental profit a few years ago, and said, can you redo that study? We did this, and I just showed you the redo. But they also wanted us, can you take it further and estimate the emissions from all that data traffic? So that was the next step. And the question that EDF was really interested in was truck emissions, particularly thinking about all the new medium duty traffic, all those delivery, all the Amazon packages, the big rigs, all the really heavy duty vehicles. They tend to, there's issues with trucks in neighborhoods and all this. So they're really interested in the truck question. And if we're just looking at traffic exposure as a surrogate for exposure to emissions, we can't really get the nuance of that. The light duty vehicles are pretty clean. The trucks emit a lot higher rate. So it'd be better if we could both split out where the truck traffic is and stuff, and also look at the emissions. So this is what we did. And so this is a slide where I try to put all the methods together. So we're doing a lot of the same stuff from the prior thing, but we have the HPMS data, the Highway Performance Monitoring System data. So we have light duty vehicle traffic, medium duty vehicle traffic, and heavy duty vehicle traffic estimates for every single roadway link in the country except for residential streets and low volume rural roads. Then we took MOVES, it's EPA's vehicle emission model. In California, you use MFAC because California has its own thing, but the rest of the world uses MOVES. And so we ran MOVES a whole bunch of times to get emission estimates for every county in the US for each roadway type. There's highways and like limited access and non-limited access roadways are a different type of roadway, and then there's rural and urban versions because the model accounts for different driving cycles on different types of roads. The model accounts for different mixes of fleets in different states, the different climate effects on vehicles, all that sort of thing. And so we estimate, and you can kind of see here, but right, we have emission rates for every single roadway segment in the country. And then we take those emission rates and we create an emission density metric. So it's like our traffic density thing, but for every census block, we estimate the grams of emissions per square meter of land. And then we'll do the same sort of demographic exercise we did before. And we kind of find the same thing, right? Because we're just taking those traffic data, basically multiplying them by emission factors. And so these are deciles, like the plots I showed earlier. And going from lowest amount of emission density to highest emission density. And as you go up in emission density, right, there's higher shares of people of color, lower incomes, and higher rates of poverty. And you can see that these are pretty significant increases as you move up in increasing levels of emission exposure.
What's that funny lift for income?
Yeah, so the income thing again is the highest, the places with the most traffic and the most emissions are also some of our biggest cities, and including New York City, where incomes are larger. So there's some of this urban effect. And we have, and I'm not showing it here, but this is like when we break it out and do it by county, we control for the average income in different places. So we've tried to look at really different ways. But
So, and then the other end that's a rural effect.
So in really rural areas, incomes are low, but you're not necessarily have, I mean, there is some like rural poverty. There's some of that going on. And some of this is reflecting the fact that in rural areas, there is less diversity to some extent, but there are rural counties that are predominantly African American or Latino. So but these are sort of national figures. So to kind of get at that nuance, we did the same thing that I showed you before. So we fit regression lines through the emission density values at the census block and these demographic characteristics to look at the strength of the relationship. And then we're plotting that regression slope and just showing the ones that are statistically significant. And it's the same story that we looked at before. This disparity in who's most exposed, least exposed, it's in every county more or less. There are some interesting things if you spend time looking at these figures that there are different patterns of exposure with the different types of vehicle traffic in different parts of the country. So like light duty vehicle traffic is a major driver of these exposure disparities in the Northeast and basically the big urban centers. And then with heavy duty vehicle traffic, we do see more sort of exposure in the Midwest and in places where there's like a lot of heavy trucking and stuff. So there's some interesting different patterns that you can see. But the main story here is just how widespread these disparities are. We also looked at the contribution of light duty, medium duty, heavy duty vehicles to exposure and these exposure disparities. And so the blue bars here are light duty vehicles, right? Passenger vehicles. And they account for about 50% of exposure. And then the trucks are the orange bars, medium duty trucks and heavy duty trucks. So you could, I guess I could have stacked them for you, but if you stack them up, they often, overall, they're about equal to light duty vehicle emissions. But for some of these demographic groups, truck emissions are the largest source of emissions by far, particularly for areas with high poverty. And so medium duty and heavy duty vehicles account for 12% of all vehicle miles traveled in the country. They account for more than 50% of emissions exposure. So they're a huge source of emissions. And they're a large driver of the disparities there. So, main takeaways from this part were trucks are a huge source of emissions exposure. And even though there's a small percentage of traffic, people of color, lower income households, again, are disproportionately exposed almost everywhere. And truck traffic is a particularly large source of high exposure faced by low income communities. And all right, so now we're at current research project. This is NCIST. This is our NCST project that's in progress, and a few sort of add-ons. This also being funded by Environmental Defense Fund and the US EPA. So the question now is uncertainty in EV adoption. So we've seen all these exposures. Electrification of the vehicle fleet is a huge opportunity to reduce exposure to vehicle emissions and to address equity, these environmental justice concerns and equity concerns. We hear from different advocacy groups talking about wanting to electrify vehicles in disadvantaged communities or overburdened communities in hopes of addressing what we've just seen here. So one question that we've had is what do the trajectories look like? We can say in 2050, when a whole bunch of the vehicles will be electric, things are going to look hopefully pretty good. But that's 2050, and it's 2024. And so it's a long time before we get there, right? And so what happens in between? What does that look like? And then given there's a lot of uncertainty, right, what does that mean? What do different pathways look like, right? And there is a lot of uncertainty, right? There's Toyota wants to build hybrids. I just bought one of these. And so now maybe people really do want electric vehicles. Electric vehicle sales are doing great. Now we've got, right, our new leader, right? Maybe we're just gonna tank the EV market. Who knows, right? Ton of uncertainty. So we wanted to look at what different trajectories mean, and we want to look at and ultimately quantify the health impacts of a slower rollout of EVs or a faster pace of adoption. And we haven't got at the health impacts part yet. We're working on it. So you're not going to see that today. So if you're hoping to see how many people's lives will be saved or how many people we kill if we go too slow, those numbers, you're going to have to wait until like spring, maybe tier. But I'll talk about what we have so far. So the questions now are looking at how does exposure change over time? What's the impact of slower, faster adoption rates on exposure and equity? And ultimately, we're going to estimate the health impacts of this. So we had to do a couple things to do this forecasting exercise. First thing, we have to figure out where people will be, right? So we're looking at exposure. So we will estimate future population by at the county level and then downscale it to the block level. We have to project for traffic. And we need to estimate the emission rates of that traffic going into the future, including the emissions of the internal combustion engine vehicle fleet and the EVs, which don't have emissions, at least exhaust emissions. So those are like our three main tasks. And so for population projections, we use the work of Hauer. This was the paper, it's published in Nature Data, which is this data repository journal. It's kind of neat. And he created county level population forecasts out to 2100, I think. And we used the sort of middle of the road forecast. So this is how we're going to, and so we grow our block level populations from the 2020 census using the growth rate from these county projections. We use the same HPMS data that we've used in the prior studies I've shown you, but we made one change. We found a better way to do our truck estimation modeling. So medium duty and heavy duty vehicles, again, that data is only sampled, so it's not collected on every road. So we used a random forest regression model to better fill in the gaps, basically. And I'm not showing you all the fitting and stuff, but it did a much better job than our prior method, and other papers used least squares regression. So, but we're using this as our baseline traffic data. And then we're growing that data using the annual energy outlook forecast from the Energy Information Agency. I see they have this. So a baseline expected national VMT growth. And we use that to estimate, we find out the VMT per capita currently, because we have the HPMS data, so we have VMT, and we know the current population of each county, so we get VMT per capita. Then using the Energy Information Agency outlook, VMT for the whole country, we divide that by the population of the whole country going in future years to get the growth in VMT per capita. And then we use that information to estimate the future VMT for each county. So accounting for, we have the county VMT per capita, we know the growth in VMT per capita for the whole country, and then we have the population projections for each county. So you can put it all together, you don't have to trust me, it's not making sense, and estimate the future VMT for each county. And then we use that percentage change, that growth in VMT, to grow the VMT on each link, roadway link, up to these different future pairs for each county. I showed the math, but it's just even more confusing. We can talk
And I'm
about
sorry, what's the source for the VMT per capita by county?
Yeah,
That's EIA?
so the EIA is just a national VMT projection. That's the best data you can get. But we start with a county VMT per capita. So we know the population of every county from the census, and we know the VMT from the HPMS, traffic data. But we know that for 2020.
Well, that's traffic. Yeah, I guess it's
VMT.
converted to VMT in the area.
Yeah.
So it's not VMT that the county people are traveling, but it's the VMT that they're exposed to.
Yeah, this is just on the roadways. Yeah.
It's really confusing because usually when we said VMT per capita, we're talking about how many VMT this person.
Generates.
Yeah.
This is
So
how
we're,
many VMT this person is exposed to.
yeah, so we're summing all the VMT, all the traffic on the links within a county, dividing it by the population of that county. And because then we have county population projections, so we can multiply, population projection on that VMT per capita to figure out how much more VMT, but we also turn this energy information agency, the VMT forecast, into a per capita forecast. So we can also figure out that they're also expecting higher VMT per capita up to some point, and then actually it goes down. So we're accounting for that too. So it's a bit of, we're upscaling, downscaling things. It's a little wishy-washy, but this is what we do when it works. So, we have a paper, it's in TRB, but I have all the math. Let's see it. I can give it to you. And we do this per capita, we figure that the growth in population is probably highly correlated with growth in light duty vehicle traffic. But for heavy duty, medium duty vehicle traffic, that doesn't really hold because trucks just travel through places, it's more complicated. So we just scaled all medium duty and heavy duty vehicle traffic, all those links equally based on national forecasts of heavy duty, medium duty truck traffic. And that's the best we can find. We can come up with anything else that would be defensible to do something more grand. So,
How about the shift toward more like heavy duty or bigger cars and the change in the fleet in the
fleet, yeah. So the fleet gets handled in the mission factor part we're gonna get to. So this is just the amount of traffic broken into 3 general classes: heavy, medium, and light duty. And the forecast we have from the Energy Information Agency gives us a forecast for heavy, medium, and light duty. So that's kind of what we have. Now the fleet, the composition of those 3 vehicle classes, we use information from the MOVES, US EPA's MOVES emission factor model, which has a fleet turnover model in it and has the the distribution of model year and the different vehicles within those classes going out through this study horizon. And so we just use the defaults. And it includes default assumptions about the penetration of electric vehicles. It's right here actually. And so that's our baseline. So we just run EPA's MOVES model. They assume this amount of penetration of electric vehicles over through 2050. So that's our baseline. And then we created an optimistic scenario where we assume greater EV, greater adoption rate. And this was this is really Meg's work, but they looked at a bunch of literature and looked at a bunch of other people's curves, probably some of yours, other people in this room, and we just kind of, said this looks like the optimistic scenario. This is what people say we need to do to stay with our these common climate goals. And then when I was pulling these slides together, we hadn't done the pessimistic scenario yet, but I have the results for it. But I didn't have nice slides like this because I don't make these things. I just do this too. But we have a pessimistic scenario too. I'll show you the results, which was what Meg describes it as basically what the vehicle manufacturers think will happen.
What's that percentage for LCV?
There's what the agency thinks, what the advocates want, and then there's what the manufacturers think. So we have a range. We have these 3 scenarios, and we have a 4th scenario we constructed based on we were presenting this out in Denver, which was someone's So what does it all look like if we just assumed a no EV future just for comparison? So we did that too. So we have these scenarios. And then we calculate the emission rates, same as we did for the prior work I showed you, except that we then create different EV scenarios by just assuming some greater proportion of the vehicles have no exhaust emissions. And so so we construct the emission factors that way, and then we assign all these emissions to individual road.
Yes, Greg, the EV ratio, is it also county level?
Yeah.
Yeah.
Yeah, so, well, I mean, so we don't have, Moves has its EV, I showed those national curves, that was just the average, but in the model, it's all at the county level. And how EPA and how they came up with it, I don't know, but it's a stock turnover model, so presumably, it's, the fleet would turn over a little slower, faster.
But do you see a big difference on section 177 versus the rest of the country?
We haven't looked at that detail.
That's where most of the EVs will be.
And since this model is not used in California, I'm interested to see how that works too. But we haven't. There's a lot of data that came from this, and this is like all pretty hot off the press. So I haven't dug into all those details, but that's a good question. We do our same emission density thing again. This is just a different example of the calculation of emission density, and create this graphic just to reinforce the point that we create this buffer around the census blocks that we're estimating emission density for, because a lot of census blocks are defined by roadways, and so the block itself has no roadways in it. So we draw this buffer around it to make sure you capture the roadways surrounding it, because of course the emissions they actually move, right? So that's kind of how we do these different parts of the task here, forecasting out at a pretty granular level out to 2050. And so here's sort of level thing. So the baseline scenario, what's just baked into EPA's model, their best guess of what might happen. There's an 88% decrease in average emission density. And it's hard to see on this screen, but so where the emissions persist are largely along these interstate highway corridors, right? And so keep that in mind. And then we'll look at, so that was NOx, this is particulate matter, fine particulate matter. There's a 53% decrease in fine particulate matter. And where the hotspots remain are in the city centers and less so on the interstate highway. So there's two different sort of patterns of how the emissions decline. And this, these maps too, they're obviously not very high resolution here, but right, this is all data at the block level. So it's really detailed. And so if we dig into this and look at the changes over time, for NOx emissions, right, trucks are going to become the dominant source of those emissions. I mean, they already are. If you add medium and heavy duty trucks together, light duty emissions will be falling over time. But what's really interesting is looking at particulate matter emissions. So today, light duty vehicles and trucks both count for about 50% of fine particulate matter emissions exposure. So if you add, these are both around 25%, being 12–50%. And those will just continue to decline, while the share of the exposure for light duty vehicles is going to increase. And this is caused by growth in VMT from light duty vehicles and the fact that electric vehicles still have tires and brakes. And tire and brake wear emissions are the predominant source of particulate matter from light duty vehicles. And so as we move to cleaner vehicles, those will be the predominant sources of exposure. So I've shown that here. Brake wear and tire wear emissions are going to increase with increasing VMT over time. while exhaust emissions come down. And right, the brake and tire wear emissions from trucks don't add up to as much because right, it's only like 10% of the truck. We have this interesting thing, and that's kind of like another way to look at this over time. We're looking at the NOx emissions exposure, and it decreased by about 88%. And it's pretty big reductions from each source. And yeah, so the amount of emissions and exposure both go down by about 88%. But for particulate matter, we have a 50% reduction in the amount of emissions, emission density, but the exposure only drops by 30%. Because those remaining hotspots are where all the population growth is also going, right? This is the emissions remain in urban areas, whereas those, and so we don't, while there's emissions are cut in half, the exposure is staying high and light duty emissions are actually increasing. And so if we look at sort of the equity concerns here, okay, we, of course, the disparity in emissions exposure remains over time, though, right, the magnitude of difference gets really small in the case of NOx. Emissions are so small, the exposure is so small. But for PM, emissions go down and then just sort of stabilize, and right, there's not a huge improvement in the disparity in exposure there. And so if we look at our base, so that was all for the baseline. If we compare baseline emissions to our optimistic scenario, right, we could get in the optimistic scenario additional 56% reduction in NOx exposure, and an additional 12% reduction in PM exposure. And you can see that it's kind of varies across the country. You can kind of look at it this way as well. The solid lines of the baseline, and you see over time how in the more optimistic scenario, you get those additional reductions out in the later years. This is a comparison of all the scenarios we've done so far with a baseline we constructed of an only internal combustion engine future. So we just turned the EVs back into ICE vehicles, we just got rid of them and scaled stuff up. And the pessimistic and the baseline scenario kind of look similar, and optimistic scenarios quite better. And this is another way to look at that data. And what's really interesting here, that was, and I have to really thank whoever it was at the conference where we presented this, that suggested the ICE scenario, because it highlights an important point here, is that a lot of the emission reductions we're seeing are being driven by increasingly clean internal combustion engine vehicles. These are our vehicle emission standards are driving most of this reduction. And the turnover in the fleet to cleaner vehicles, meaning more stringent things. So you can see the EV, the increasing penetration of electric vehicles certainly has an impact, right? But this biggest impact is actually just the cleaner internal combustion engine vehicles, right? And so just a takeaway here is that maintaining these vehicle emission standards is critical for reducing exposure. And those are, are obviously under threat now, right? They're probably going to be rolled back in a few months. And so EVs can help, but, it's going to take time to turn over the fleet to adopt electric vehicles. But the big change is being driven just by the turnover of vehicles in general that meet higher vehicle emission standards. And EV adoption and these vehicle emission standards cannot keep up with the increasing amount of VMT in the light duty sector, because the tire wear emissions, the brake wear emissions, will eventually, so much of that will result in increasing particulate matter exposure. And so we have to think about like, today, the focus is on dealing with trucks. They're driving most of the exposure and some of the biggest equity concerns. But looking out further, we have to continue to think about travel demand, light duty vehicle traffic because of the tires. And tires you might be thinking like, is it really a huge source of emissions? How big is it? The largest source of microplastic in the oceans is tire parts, right? These things, you're just, you gotta buy new tires or like yours. It's going somewhere. It goes into the air and then it rains down and pollutes our water. It turns out there's some sort of antioxidant that they use in this rubber that is extremely toxic and has bioaccumulated in all of us. And this was raised at TRB last year. Yeah, I guess it's really bad for some aquatic wildlife, but it's probably not great for us either. So these particulate matter from tires, particulate matter itself is toxic, is harmful to us just because the particles cause inflammation. But also what these things are made out of, I don't really know what brakes are made out of, but it's probably nothing you want to eat and breathe in. And then the tires are pretty toxic. So it's actually a pretty big deal. And regenerative braking and stuff might be reducing brake emissions, but EVs are heavy. And so tire particles.
It's really important. I think that the braking emissions are way overestimated for EVs, and I know the sources that you're citing, and they are not taking all region into account. And everyone who drive EV for years, that you never replace brake pads. So where the wear and tear comes from, you should never replace. People own EVs for 10 and 12 years now, and they never replace brake pads, so they're probably much lower wear and tear.
Yeah, and so the Moose model we're using does not have the latest and greatest research on the brake wear, but on the other side, the tire wear emissions are probably underestimated.
Yes.
Yeah.
I'll just make the point that I worked in tires, that the Ford company I worked at could not have been more pro EVs. They loved nothing more than electric vehicles. They viewed that as a very good revenue stream. People replacing tires every 25,000 miles and stuff. So,
That's not.
and more expensive tires. So I would.
Well, so these are evolving things, and right, so the other thing that are happening though, right, I just bought new snow tires, as you do in Vermont, for my new EV. But they're making them out of different compounds and other ones to hopefully last a little longer and stuff. So I think there will be innovations, but so there's certainly, right, we're looking at 2050 here. We've got population projections, BMT projections. Maybe not the latest and greatest emission factors for any of this stuff. It's all really tricky stuff to do. So there's certainly a lot of uncertainties in these numbers, but they, I think, give you a sense of what some things to think about here for policymakers and for researchers. But trucks are a big deal. We kind of knew that, but now we can really see just how bad. We can debate about the emission factors for tire brake wear, but they're a pretty big source. And if we expect BMT to grow the way we think, that'll be a growing source. So, that's all I got.
No questions? Okay.
Oh, just continuing on with the tire and brake emissions. I think I was reading an article that was sort of showing how the results of some study showing kind of a similar thing was maybe misused, I guess, or it was used in the name of like saying bad news about EVs. And the authors sort of like clarified saying that like the tire and brake emissions are just a larger share of the exposure from EVs, but sort of it takes away or possibly could like the comparison to what it would be if in an all ice scenario. So I think, maybe like.
Yeah, so that's a good point, right? These are shares, right?
Yeah.
But right, we do see it when you put it all together too. It does result in we're looking far out, it's kind of creeping up too. But yeah, it's not. the net benefit, I mean, if we were to compare, just to like ice, right, it's still better. We have that right here, that the EV scenario, heavy EV is still better than the ice only. So even though we're shredding more tires, we're still net better, which I think, I remember that study.
But it's a good warning, there's sort of a limit and some trade-offs
Yeah,
we
that's,
should not ignore.
it's, you don't wanna take it and just say, maybe we shouldn't have EVs because there's more tire particles, but it's cautionary that we can't, and this has been the message, pretty consistent, that EVs won't solve all our problems either. They're not, we have to address demand to zero greenhouse gas emissions, but if we are concerned about exposure to criteria and toxic air pollutant emissions, it's a similar story. And we're not even talking here about like the resuspended dust and the actual pavement and everything. That's a whole other thing. That's not even accounted for in this type of model.
Well, I want to thank you for sharing very clearly your construction of this model. I think this is a great example of, putting together data that we have and projections to build a tool that enables you to do some scenario testing. So I think I have two questions related to that. One is, do you have any thoughts about turning this into a publicly available tool where people could play around with some different kinds of assumptions? And then, well, maybe you can comment on that and then have a kind of a more general question.
Yeah, so our we have a vision to turn this into a tool that can be used, possibly like an interactive website, where you could look around at some scenarios. Probably the first version of that would just be pre-computed stuff like from the paper, but you could zoom in and see stuff. We've also been talking with some potential research sponsors about the idea of creating an actual tool to be used for regulatory and policy analysis. But I have that meeting in a few weeks, so I don't know when it's going to happen.
Well, that's cool. A little scary, but cool.
Yeah, well, we've been working with the US EPA on this work for their regulatory applications. And so, and EDF to deal with the community outreach and advocacy around, these EV strategies and where to put them. So there's a lot of interest from different sides and what to do. And so we definitely want to create this, like the journal articles, not the end of it. We want to create something, and we've been doing that using some of our NCST funding at UVM to create interactive online tools from some of our projects. So this one, you have a new grad student that is trying to figure out how this project will end up online.
Oh, great.
That's the project.
Well, and I guess my follow-up question is just a reflection. I'd love to hear your thoughts about doing this kind of work. I don't know what everybody out here is thinking, but you build, it is a very useful tool, but it is also built on lots of assumptions. And it's really, it's scenario testing, it's not forecasting. So I don't know if you have kind of some thoughts about this whole just modeling.
No, I have lots. Yeah.
Yeah, okay.
Right. So.
Because we do a lot of this kind of work around here too. Yeah.
Yeah. So this is, as we've talked about, there's a lot of assumptions, and some may be better than others. And we, I cobbled together a bunch of different projections and things, and tried to find the best information, put it together in a thoughtful way that's hopefully not overstating what we know, and is at a resolution that's policy relevant, but not, but hopefully there's enough truth to it. So one thing that's important in this work is the absolute numbers. So if we go back and look at these maps have estimates of emission density at the census block level in grams per kilometer squared. if I go out in 2050, any of these census blocks, I doubt whatever I would measure then will add up to what I'm projecting, right? What odds? This type of modeling, in my opinion, that of other people that do this type of work and the EPA itself have stated it's generally thought that it's most useful in a scenario analysis, the application where you're comparing multiple scenarios together. So we think we have like the dynamics of the system, right? The way things move different ways. And that comparing differences among the scenarios is what is sort of the most valid thing to do with something like this. But pointing to like, because we have some people we work with really interested, knowing like, they'll go point at a particular block group on this and say, well, they're going to be really highly exposed, so many deaths, and want to go start some big, lawsuit or advocacy campaign, something like that. But we have to say, no, you can't. That data point's there, but that you can't use it in that way. What you could do is say, okay, blocks or this neighborhood region like that, under different scenarios, we would expect the exposure to go down or up by, a lot or a little. Like that's a valid thing to do with this, but not use the numbers. And that's the same thing with like travel demand modeling that we do. MPOs they all run these big travel models to project the amount of EMT and mode share and the speed of the traffic on individual roadway lengths, right? And those operate at a much more detailed level than what that you can't do that at the national scale, which is what we did. But those travel demand models are really uncertain also. And unfortunately, they get misused all the time, particularly a lot of my work with the nonprofits. I do a lot. When I worked at NRDC and afterwards, I've consulted for Environmental Defense Fund and the Sierra Club on different highway project widening lawsuit things, and they do my air quality analysis, right? And there was this case in Colorado, the widening of Interstate 70 through downtown Denver. And there was a lawsuit brought, and they're arguing over the model concentration of particulate matter along the highway under the build scenario in 20, whatever, 40, 50, whatever the horizon year was. And it was like a 100th of a microgram over the National Ambient Air Quality Standard, right? And if it goes over this, you can't do the highway or you gotta find the vehicles. So we're fighting over that. But this is like a 20, 30-year projection, a model. And they use moves, which, Gil's told us all the emission factors aren't perfect in there. And back then, they didn't even have EVs in the model. And the traffic volumes are projected, the traffic speed calculation there's so many uncertainties. And to be fighting over 100th, this is like a fraction of a percent, was crazy. And it came down to, when we sorted it out, you have to put receptors with modeling every 25 meters along the fence line of the highway. If you started where you put your first receptor and then count 25 meters, if you create a different starting position, you just miss that high spot. That's how small this number was. This is totally inappropriate. These models are never built to do anything like that, but that's the way the Clean Air Act works, apparently. So we do have these tools that get misused like that. So usually when you work with transportation planners and MPO, they hopefully are developing several scenarios and doing more of a relative comparison. But yeah, so these complex models get used for questionable things. Doing your own work.
That's students first.
Outside of the projection, like mapping and everything, is there any plans to have this like integrated into like Cal screening for the state? Because I mean, they have PM 2.5, diesel, particulate matter, all sorts of like emissions data for census blocks, but this seems more like comprehensive.
Yeah, well, so this is nationwide, so maybe it'd be something more like a EJ screen or something at the national level, but I think I'm not super familiar with Cal screening, but I'm assuming the emissions in there are like present day emissions, not forecasted for.
Yeah.
and then I don't know what the source of those are. Yeah, so one idea is to create a website where you could see this data and do comparisons and whatnot. We are also planning to do, so part of this that we haven't done yet is we're going to use health impact functions, like from BenMap if you're familiar, but we can turn changes in concentration into changes in health outcomes and health risks. And to do that, though, we're doing work right now where we're taking our emission density calculations and correlating them with modeled changes in air pollution concentration values, because we want to show that changes in emission density when done at a small enough scale are good approximations of changes in concentrations. And if we can show that, then we'll be able to use our emission densities in existing health impact functions. And the problem with, you might say, why don't you just estimate the concentrations? Because that modeling is really complicated. And it takes a huge amount of computational resources and time. And so you couldn't do a bunch of scenarios. You couldn't do a national scale thing. So that's work we're doing right now with our NCST funding. That's the next piece of this. And so by sometime in the spring, I'll be able to show these maps. Instead of saying NOx exposure, this will be the number of cancer cases avoided or caused, heart attacks.
And you're gonna be in trouble.
I like to get in trouble.
Yeah, that's big impact.
But that-
You put it
that's-
in those terms.
This is what I tell kids, like that's the New York Times front
Yeah.
page story, and that's what we're going for here, is to try to get this stuff out and to be used.
Students first, sorry.
Yeah, so I have a couple questions about the factors you're using in this model. Is it relevant to include projected land use change, especially when it comes to urban tree cover for like measuring emissions and exposure?
So I'm gonna answer a different question, but that scale thing, like, so yeah, trees, right? There's research showing that you can, use trees to filter out some particular matter or something, right? And it can also just act as a wall of direct exhaust. So we can't look at that scale detail when we're working at this level, right? And so there's a whole nest of different types of models as you drill down to specific things. And like, so other limitations though, that's one, right? We're not looking at like tree canopies, we're not looking at street canyons. We're also, these are ambient concentrations, but we're all inside right now, right? The air is probably being filtered. So, and then of course, we're assuming, we're looking at these inequities based on where people live, but people move around all day, right? Spend your time working here, going to school there. So there's a lot of things we're not accounting for. And I and others have done other research looking at how exposure looks different if you account for where people spend time. We've done that modeling using activity-based travel models. And like the numbers can look totally different. So there are other people that measure inside concentrations and outside. Yeah, that's a good question.
Do you think you could also integrate noise pollution into this model?
That question gets asked, yeah, it's come up before from other people. I mean, I've never modeled noise, but I assume I could find someone that knows how to do that or look it up, and I'm sure there's some, the traffic data, I assume it's one of the main inputs.
Yes,
Would
you've
the
got
model allow
traffic
this?
and speed.
We don't have speed,
Oh, you don't have.
but that is what we're working on with US EPA right now, is to put speed on these traffic volumes and then have speed adjusted emission factors. But that's a big
Yeah, noise.
So you mentioned that like the PM2.5 emissions only decreased by like 30%, according to
The
projection.
exposure, the emissions go down 50, but the exposure 30.
So why is there a discrepancy between the exposure and the emissions? And also, is this like accounted for like the effects of regenerative braking and other issues like maybe driving habits and etc.
So, okay, yeah, a couple questions there. So the first one, the emissions, so this is just what the emission concentration or density look like. So they go down, but where the hotspots remain are urban centers, which is a different pattern than for the NOx emissions, where the remaining hotspots are more along some of the travel corridors. And so, so the remaining emissions, these hotspots are also where there's more population. So exposure remains somewhat higher. So there's a little mismatch between emission reduction and exposure reduction. And we don't account for, as Gil's pointing out, like the regenerative braking isn't this EPA model. This is what's used for regulatory purposes, but it doesn't, not all the science, there has to be a robust amount of testing and validation, and especially in a model that's used in regulatory purposes before that's going to show up. So the model's a little behind the times in accounting for that with EVs. But it does, in a very general way, account for different driving patterns. So in moves, there are different drive cycles that are attached to different types of roadways. So an interstate highway is assumed to have more constant speed profile and higher speed. So that is accounted for, and a local street is encoded differently in the model, and it's assumed to have more stop and go patterns. They have these standard drive cycles that are baked in. But what's not accounted, so some of that's accounted for. What's not accounted for, though, is that, you know, the might be terrible congestion in San Francisco and not so much in some other city or some road, and that the traffic congestion levels change over the time of day and all that. So that level of congestion, traffic dynamics is not in this version, but that's what we're trying to work on, because it can make a big difference. But to project the speed now and into the future for every road is a little bit challenging. And actually the bigger challenge is estimating the emission factors, because running the MOVES model for all this takes a long time. Now having to break out all the results by speed band will take an even longer amount of time.
I might be missing something on the sequence, but and you will help me here. You're starting with the traffic data, and how much of the VMT is happening on surface road and is not counted at all by the model, and happen, let's say, within the county, within the centroid. And then it's have a multipliers that have much more emissions, for example, cold starts.
Yeah,
The NOx effect will have. So I think that unless I'm missing something, I think that the model is missing a lot of the local emissions before we even go into speeds and so on. And I wonder if you can calculate what % of these emissions are missing.
Okay, yeah, so 15% of overall VMT is missing from those local residential streets and rural roads.
Then
So we
cold
got
start.
most, we don't have the cold start, right? The off roadways or emissions, the start stop and that, and extended idle. That's a little bit, I mean, we can do it, but that hasn't been the focus of what we've been doing. That would be typically more important when going into doing a whole emission inventory and then going into like photochemical modeling, like regional scale emission analysis, which is also a potential other direction of this work, but that part didn't get funded, so. Go there
That's a
again.
good answer.
But yeah, the start stop. And so these are the on-network emissions, on roadways, been the focus of this work, and the sponsors have wanted to see that, and there's good reason for it. But when you start and stop your car, those are another part of the emissions. And we generally estimate those by just looking at like population density and just sort of scattering those out. But you're right, that's missing.
Is your like EV adoption prediction, is that just a national average, or does it take into account certain areas or like sociodemographic groups that may be more or less inclined to adopt?
It's a national projection, but it does get geographically altered because there's different fleet turnover in different counties in the model. But it's not accounting for the fact that like people in California and Vermont might adopt EVs at a quicker rate than some other place. We don't have,
You could build in
We could.
state level factor.
you can, this is the type of thing you just keep I've been doing since I started on this long time, I just keep adding more stuff onto it, trying to build, so, yeah, it's lots of great ideas. All welcome to come to UVM and help plug more things into that.
Or partner.
Or
between
partner.
UC Davis and
Or
UVM.
partners.
There was another question.
So, could it be relevant to incorporate power plants and
Yeah, that was the part that was not funded. We were like there was this big competition to do this, but yeah, there's still interest in doing that and looking at that. We'll likely do that at a future part of this project, but yeah. So if we, it's particularly relevant to looking at the regional scale emissions would then be accounting for the fact where the electricity came from and the change in the power generation side and accounting for the exposure to those emissions, but those become regional emissions. So then we have to do chemical transport modeling, which is a whole nother thing. That's at a totally different scale. And so I had to collaborate with other people that know how to do this.
All right, Lana, Tricia, did you have a question? Last.
Yeah, I guess I was wondering, have you thought about incorporating wear and tear on roads? Like what percentage trucks account for, what additional impact EVs could have?
I have not, but that's a great question. I've done some of that work like in some litigation I've worked on because it comes up as an important thing, but the existing like methods for modeling that wear and tear roads are pretty simplistic. So, and maybe there's undoubtedly more research being done on that now with the whole EV question and heavier vehicles, but I haven't looked into that in much detail, but that's certainly something that could be incorporated.
Well, we do have a pavement research center here.
Yeah.
Some people doing
You
life
got the
cycle.
thing that goes,
or-
runs over the
Someone needs to.
That'd be great. Well, it sounds like you have a lifetime of work ahead of you.
You got, I don't know what you're all doing your thesis and dissertations on, but you can each pick a piece of this on.
Yeah, all right, one last.
Okay, so the last question, actually, her question just made me realize, I wondered if you could integrate into this bicycles as a way to reduce PM2. I don't know if that would be too complicated, but
Well, or I was wondering about bicycle exposure too. I mean, people do that.
yes.
It's like if you do buy an EV, just don't drive it and ride a bicycle on the road.
Well, okay, so no, this is a good question, right? So this is somewhat the point of this is we're doing this big national nets. We're looking at these different scenarios. We're pointing out that we're looking at different EV penetration rates for this specific case study because that's one of the things of the day. But we could also use this same framework to look at different VMT reduction strategies. I mean, there's no like behavioral component to this, obviously, but if we assume what if in metro areas we could get a 5% shift to active travel and in rural areas 1% or something. I mean, we could do that and look at the impacts, but there's obviously there's no travel demand model baked into this. We can't look at put proposed bike infrastructure on this map and model. I mean, you could, but but you could do these different types of scenarios. We're doing an EV one here, but you could look at different population growth scenarios. You could look at what if there's more growth here, there, urban, rural, more active travel transit, and how that would, you'd have to come up with your own multipliers to dial the VMT down. And when we get the speed dynamics into that, that'll make it really interesting. We could really see if we reduce VMT, how that could also reduce congestion, which could also reduce emission factors. Or you could go let then we'll have to put the induced demand calculator.
Yeah, we'll just put it all together.
Model will answer it all.
Yeah. Well, thank you so much for sharing this work. Really, obviously important work, and wish you the best with it. And I suppose we can follow up with you. So, thank you very much.